For this lesson, we're going to be taking what we've talked about with regards to the exponential and logarithmic functions. We've looked at taking the derivatives of those, and one of the natural topics that would follow from there is the idea of optimization. We're also actually going to be looking at this in terms of curve sketching, because it turns out that curve sketching is actually the more involved operation out of the two of them. So optimization is, in many ways, it's actually a subset of curve sketching, in the sense that there are more operations you have to do for curve sketching than to actually do optimization. So we're going to do today's lesson, we're going to illustrate today's lesson by actually performing curve sketching. In general, though, if you're solving an optimization problem, particularly an optimization word problem, it's worth a quick review of some important steps or strategies that you might want to consider. A diagram is always a good idea if possible. We need an equation in a single variable. All of the calculus we've learned so far only applies to a single variable. That means taking the derivative. Looking at the domain of the function. Are there any restrictions? Are there any asymptotes or holes? Taking a look and finding, once we've done our first or second derivative, we're going to want to use some combination of those to both identify absolute max or mins from any extrema we have, or any endpoints. And of course, for endpoints, we also need to understand the domain. The extrema are going to come from our first derivative test, and then we classify them using either the first or second derivative test. And don't forget to answer the problems. Some of the particular considerations that might apply to exponential or logarithmic functions. We need to remember the specific rules we have for exponential expressions, the laws of logarithms, the laws of exponents. When you are solving, don't forget this idea of taking the log of both sides. So if you've got an exponential equation, I don't know, let's say something like if you have 5 to the x is equal to 10, one way that you can solve this for x is to take the log of both sides, and that will allow you to use the laws of logarithms to isolate this x. And don't forget our limit behavior at any asymptotes or at the endpoints at plus and minus infinity. So that's what this is referring to. At any asymptotes is 1, and then we also want to consider our limit behavior at plus and minus infinity. That's going to tie back to the domain. If we have a restricted domain, it may not be appropriate to take a look at the limits at plus and minus infinity. So let's go ahead. We're only going to do this one example, but you're going to see that this is fairly involved. There's quite a bit that we have to do here. So the first thing we're going to do is we've been asked to use the curve sketching algorithm to sketch this. Now, the curve sketching algorithm is a guideline. It's not a hard set of rules in the sense that you have to follow it in any particular order. You need to make sure that you enlist the tools that are required for you to get the job done. So I'm going to start here by taking the first and second derivatives of the expression that I have. So my first derivative, y prime, I have x squared multiplied by e to the 2x. So this is a product rule because I have two distinct terms here. So I'm going to take the derivative of the first, which is 2x, multiplied by the second, unchanged, which is e to the 2x. And I'm going to add to that the first term, unchanged, which is x squared. And then the derivative of the second term is going to be a chain rule derivative of this exponential function. So the derivative of e to the anything is e to that same thing, but the chain rule says I also have to multiply this by the derivative of whatever was the argument of the exponential function. So in this case, the derivative of that is equal to 2. And now I'm going to do some simplification. So I end up with, I'll just rewrite that first term, 2x e to the 2x. And then I bring over this 2 in front, so I end up with 2x squared e to the 2x. And it wouldn't be a terrible idea, since I know I'm going to be interested in curve sketching, I'm going to be interested in solving this first derivative for 0. So since I'm here, I'm just going to go ahead and put this into a factored form. Common factor, there's a 2 common factor, there's an x common factor, and there's an e to the 2x common factor. And that's going to give me what's left behind here is just going to be a 1 plus an x. So that's good enough for this. I can work with this and I can solve this. Now let's move on to my second derivative. Now where you start with your second derivative is up to you. This is actually a pretty nice form that I have here, but be aware that I actually do have, if I use the form that it's in right now, I've got 1, 2, 3 distinct factors that I have to take the derivative of. Now, if you were to go up to the previous line, you have 2 factors here and then 2 factors here. But 3 factors means I'm going to have to do the product rule 3 times. Here, I'm going to do the product rule twice, but it's a little bit easier. It's up to you. You will get the same result regardless of which way you do it. Just for the sake of continuity, I'm not going to sit here and worry too much about which one I'm going to use because I don't think it's going to make a big difference. So I'm just going to go ahead and actually maybe a little bit more interesting for demonstration purposes, I'm going to take this one that is a triple product rule. Now I've spoken about that very briefly when we talked about the product rule. I gave you an example that was something like f times g times h. And if I take the derivative of that, the way that works out is it's the derivative of the first one, which is f prime, times g times h, plus the first one times the derivative of the second one times h, plus the first and the second one times the derivative of the third one. You can also show this by breaking this up into distinct pieces, but I'm not going to go through that demonstration right now. So using this model, my product rule is going to say the derivative of the first is simply equal to 2, and then I rewrite the second one and I rewrite the third one complete, plus the first one, which is 2x, times the derivative of the second one. The derivative of the second is e to the 2x times 2 times the third one, which is 1 plus x, and then plus I can take the derivative of, so I'm going to leave the first one complete, I'm going to leave the second one complete, and now I take the derivative of the third one, which is actually a trivial derivative, and that is just equal to 1. So now I've got my second derivative underway here, and once again, maybe a little bit of simplification. This line might be optional. You might want to go straight to factoring at this point, but a little bit of simplification won't hurt here. 2 times 2 becomes 4x e to the 2x times 1 plus x, and this last one is plus 2x e to the 2x. Now I'm going to factor out any common factors. Numerically, I have a common factor of 2, and I also have this e to the 2x term, and it looks like that's it. So now what's left behind is, from this first term, it looks like there's just a 1 plus x left behind. In the second term, there is the number 2, there is the factor x, and there is a 1 plus x left behind. And from this third term, the 2 comes out leaving a 1, the x is left behind, and e to the 2x got taken out. So I'm going to expand and simplify what's in that bracket now, and I end up with 1 plus x plus 2x plus 2x squared plus x, and when I combine those together, I end up with a 2x squared in front, and I've got x plus 2x plus x is plus 4x, and just the one constant of 1. Okay, so now I have the simplified and factored forms for both the first derivative and the second derivative. The next thing that I want to take a look at is critical values. Now, the reason why I found the first derivative and second derivative and put them into that factored form was so that I could solve these for 0. So for this one, I'm going to set y prime equal to 0. And here I'm going to set y double prime equal to 0. Now when I say critical values, some people refer to critical values only as the zeros of the first derivative. But what I mean is I want to find all x values where something interesting may be happening. So to my mind, we are looking for the zeros from both the first derivative and the second derivative. Those are all interesting values, whether they're supposed to be called critical values. Hopefully you understand what I mean. So these look slightly different than what I ended up with before, but the only difference really is that this factor was behind when I wrote it out before. So let's go ahead and do the first one. So y prime equal to 0, which means 0 is equal to 2x times 1 plus x e to the 2x. And that can only happen if one of these three factors is equal to 0. So we end up with 2x equals 0, which is of course the same as x equals 0. I didn't even need to write that out. I end up with 1 plus x equals 0, which means x is equal to -1. Or I could have e to the 2x equals 0. But if you remember exponential functions, the general shape of an exponential function, especially one as simple as this, is something like that. There's the y values. This is never equal to 0. And so this one has no solution. So those are two of my critical values, x equals 0 and x equals -1. When I set y double prime equal to 0, I get 0 is equal to 2 times 2x squared plus 4x plus 1 times e to the 2x. And as we've also already seen, e to the 2x has no solution. 2 is a constant, so that can't contribute. So that's only going to happen if 2x squared plus 4x plus 1 is equal to 0. Now to solve that, it's not something I can factor using an integer method. There are no two numbers that multiply to 2 and add to 4. And so the next thing I'm going to do is I'm going to look at it from the quadratic formula perspective. And so to do that, the first thing I'm going to do is I'll look at the discriminant b squared minus 4ac, and that's equal to 4 squared minus 4 times 2 times 1. And that's 16 minus 8, which is equal to 8. So that means we actually have two solutions. And so now I can proceed with the confidence that I'm not going to be wasting my time here. So quadratic formula, x equals -b plus or minus the square root of b squared minus 4ac, all divided by 2a. Since I have already calculated b squared minus 4ac, I'm just going to use that value. -b, that's going to be -4, plus or minus the square root of 8, all divided by 2 times 2 is 4. And I can do a little bit of simplification here. First of all, I get -4 divided by 4. That's just equal to 1. Plus or minus, and this is going to be the square root of 8 still divided by 4. But what is the square root of 8? Square root of 8 is the same thing as the square root of 4 times 2, which is the same thing as 2 root 2. So I can put 2 root 2 there. And I divide out 2 goes into 2 once, 2 goes into 4 twice, and so I end up with x is equal to -1 plus or minus root 2 over 2. And you could have there's a few ways you could represent this. Now this is a pretty nice form as it is right now. Probably going to want approximate values for this. So that works out to be x is approximately equal to root 2 over 2 is equal to 0.707. So -1 plus 0.707 is -0. And I think 293. And x is approximately equal to 0.707 -1.707. And that's going to be a little bit easier for when I do my interval table next to do that. So I've got 4 values here that are where interesting things happen. These values in particular I'm going to be looking for to be my extrema, my local extrema. These values I'm going to be looking for to be points of inflection. Okay, so that's the next thing we're going to do is we are going to apply the second derivative test. Now you might wonder, well, why not the first derivative test? Technically, the second derivative test is generally more powerful because the second derivative test can also be used to detect extrema. And I'm going to show you what I mean by that. So I'm specifically only going to do the second derivative test here. And so my intervals from the second derivative test are going to be based on the results of the second derivative being equal to 0. So that's the first thing I'm going to do. And I don't have any vertical asymptotes or anything like that. So I've got two values here, which means I need to have two dividers. And so one of those dividers is going to be negative 1.7, and the other one is going to be at negative 0.3. I'm just rounding those off. And then I'm going to put in my factors for my second derivative. And so that's going to be, of course, 2. I don't really need that. I'm just going to put it in for completeness. And then I've got 2x squared plus 4x plus 1. And then I have e to the 2x. And again, not one that I necessarily need, but I'm doing it for completeness just to show you why I'm doing it. So let's go ahead and put some lines in here. And you're going to see very quickly why I've said, well, I don't really need that one. And actually, you know what? One more line here just to separate those out. Okay. Now 2 is always positive. So on this interval it's positive, on this interval it's positive, on this interval it's positive. Then we have e to the 2x. Well, that's an exponential function, and it's not transformed in any way that's going to change its sign. So this one's positive, this one's positive, and this one's positive. So all that leaves for me to do is actually to pick a value here and figure out what is this factor going to be. So for example, I might put in negative 2 here. This is the interval from negative infinity to negative 1.7. This is the interval from negative 1.7 to negative 0.3. And this is the interval from negative 0.3 to infinity. So let's go ahead and put in negative 2, and I think here I'll use negative 1, and here I'll use 0. Those are all really convenient values. Negative 2 in here is going to give me negative 2 all squared is going to give me 4. And if you want to, you can always fill these in. So negative 2 gives me 4, and then 2 times 4 is 8. 4 times negative 2 is minus 8, and then plus 1. And so we have 0 plus 1 is equal to 1, so of course that's positive. Negative 1, when I put negative 1 in here, negative 1 squared is 2, so that gives me negative 1 squared is 1, 2 times 1 is 2. Negative 1 times 4 is negative 4, plus 1 is equal to, that's going to be negative 2 plus 1, that's negative 1, so that's a negative. And then 0, when I put in 0, I get 0 plus 0 plus 1, so that one becomes positive. So our results here are plus, plus, and plus, that's going to be positive. Plus, minus, and plus, that's going to be negative. And plus, 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 that's going to be positive. So what does this tell me about the shape of my graph? Positive means it is concave up, negative means it is concave down, and positive means it is concave up. Okay, so from there, you might wonder, well, hold on a second. We've ignored these values because I've identified my points of inflection. This changes from concave up to concave down. That's a point of inflection. That's a point of inflection. What about these values at 0? And I just want to explain to you, why does the second derivative test actually help us here? How does it identify, or how does it classify those? Where is x equals 0? Well, it actually turns out we used x equals 0 here. So we know that x equals 0 is concave up. Well, what does that make this point? At x equals 0, it's concave up. That means it must be a minimum. At x equal negative 1, that was right here, x equal negative 1, it's concave down. And what does that make that point? A maximum. So by working on these intervals from the second derivative and performing the second derivative test, we can automatically identify our local maxima and minima. So that's actually done. We've now classified all of our points. And from here, so concave, this one is concave up, and then this one is concave down. So we know we've got something like that happening. And then here we've got concave down to concave up. So we've got a point of inflection like that happening. Or we could have concave up and concave down. It could be this and this. So we don't know which of those two it is, but we do know that it's a point of inflection. Okay, so let's move on. Let's take a look at our end behavior. So for our end behavior, we are going to take our look at limits. Now we don't have any asymptotes here, so all we need to do, I don't want that color, we're going to take the limit as x approaches infinity of x squared e to the 2x. Now this one's actually fairly simple, because if we think about it, as x gets really big, what happens to x squared? X squared also gets really big. What happens to an exponential function? Well, that gets really, really big. So we have a really, really big positive number multiplied by an even bigger positive number. And so the result there, the result of that limit is infinity. And this is really one of the few places where you can say something equals infinity. And then the other end behavior we have to look at is the limit as x approaches negative infinity. This one's a little bit more subtle. And the reason, and I'm going to do a little bit of a side note here. So x squared gets really big. Okay? And it gets really large in a positive way. We're taking this negative, but we're squaring it. But for this one, again, I'm going to remind you of what an exponential function looks like. E to the 2x looks pretty much like the parent function for an exponential function. And so when we go to negative infinity, what does this become? This one gets really small, but it becomes a really small positive number. It stays above the y or the x-axis. Now the question becomes, in the kind of the duel between these two, this one's getting really large, this one's getting really small, which one wins? And so here is kind of the deciding concept that goes along with these. First of all, you can show this to yourself. You can put in some values for x, negative 100, negative 1,000, negative 10,000, negative 1,000,000. And what we find is that an exponential function will dominate any polynomial. So when it comes to a battle between an exponential function and any polynomial at all, the exponential function eventually is going to win. The power of an exponential function to grow, the power of an exponential function to squeeze down to zero, will completely overwhelm this polynomial once you get to really big values. And so as a result, my answer for this is equal to 0 from above. The limit here is equal to 0 from above. Now, if we were going to write this out, we'd probably want to write this out a little bit more nicely, which I've done on the next page. So we've got our end behavior. As x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches 0 from above. That's a really good way of writing out your end behavior. Notice also, I took the information from our classifications, but I've also included the y coordinates for each of these points. I'm just doing a sketch, so I don't need these y coordinates, but it may be helpful. And if the question asks you for the critical points, or the points of the extrema and points of inflection, you do need to give me coordinates. You have to give me the full points. So let's go ahead, and I'm going to do this very roughly. So it looks like most of what's interesting is happening here over on the negative side. So I think I'm just going to roughly divide this. I'll make this -1, make this -2, make this -3. I take a look, I see I have a minimum at 0, 0, and we knew that was a minimum because it was concave up at that point. We have a maximum at -1, and it's actually not very high, 0.135. But I'm just, again, for the sake of my sketch, I'm going to put a maximum there. Then what else do I have? I have a point of inflection at -0.3, which is about here. So that means when from here down to here, we have this point of inflection. And then to the right, there's nothing else happening to the right by way of features, but as we go right, we know that we go to infinity. So what it means is this concave up continues to infinity. And so that's what we end up with on the right-hand side. It may be shallower than that, than what I'm showing, but that's still concave up the whole way. And then over here on the left-hand side, we do have another point of inflection around here at -1.7. And so what that means is that this concave down part continues until there, and then it changes to concave up. And it does that all the way to -infinity, and during that time, it approaches 0 asymptotically. This is going to be really hard for me to do. So let's see if I can draw a nice smooth curve. That's not terrible, heading out to infinity. So the important thing is here we've got our local maximum, we've got our local minimum, and it turns out this is an absolute minimum as well. This is still a local maximum. There's no absolute maximum because this goes up to positive infinity. I've also included a computer-generated version of this, much nicer than the one I did it, but you can still see here's our minimum, our absolute minimum at 0, 0. Here is our local maximum at -1. Here is that point of inflection where it switches, and over here we've got a point of inflection where it switches. Now I've also included, I'm sorry if this appears a little bit cluttered, I've included the first and second derivative graphs on here as well. So for example, the first derivative graph has a 0 here, which corresponds to our minimum. And the first derivative graph has a 0 here, which corresponds to our maximum. The second derivative graph has a 0 here, which corresponds to the point of inflection. And the second derivative graph has a 0 here, which corresponds to the other point of inflection. There's a lot of work involved in that example we just went through, but hopefully it all makes sense in the end. For your assigned work, I'd like you to specifically take the time to read through the examples on page 241 and 240 to 244. I don't often do this, so I wouldn't be asking you to do this if I didn't think there was some value in going through them. And then some assigned questions to keep you entertained.